So this is Chapter 10, Interactions and Potential Energy. So everything we learned in Chapter 9 we're going to use. Now this is very misleading. Look, there's only 3 learning objectives. So you think it's going to be a short chapter? Wrong. This is a very, very long chapter. So here we go. We want to expand the basic energy model by introducing potential energy. Learn to use and interpret energy bar charts and energy diagrams. Develop a complete statement of the energy principle and apply it to isolated systems in which energy is conserved. All right. So let's just review before we do anything. So this is from the last chapter, right? This is the basic energy model. So energy is a property of a system. You've got to remember that system, right? Not just an object like with force diagrams. We have a system. Within the system, you can transform energy. You can transfer energy between the system and the environment. Forces do work on the system. Work is positive if energy is added. Work is negative if energy is taken away. The energy of an isolated system, one that doesn't interact with its environment, doesn't change, so it's conserved. So we're going to hear this word a lot, conserved. It just means no matter what you do, whatever is conserved doesn't change. The energy principle, the change in energy of the system equals external work. And this model fails if there's energy transfer via thermal processes like heat. So we're not talking about heat at all. All right, so let's talk about, we introduced potential energy last chapter, but we want to talk about it a little bit more now. So here's a mousetrap. So let's say we set it, and then we take a pencil and we set it off with a pencil. So it's going to snap. The trap's going to snap and probably break the pencil. Now, where did the energy come from to break the pencil? Well, the spring, right? The spring. Well, would it work if I didn't set the spring? Obviously not. So therefore, I am involved, right? I'm involved. There's an interaction between me and the mousetrap, or the spring, okay? And the interaction involves energy. Here's another one. So this is Tiger Woods dropping a ball. I don't know anything about golf, but the caption said he's doing something against the rules. Okay, whatever. But anyway, so he's dropping the ball. And as the ball gets further and further away from his hand, it gets faster and faster, right? So the kinetic energy is increasing. Why? Why does it go faster? Why does it gain kinetic energy? Well, because the Earth is pulling down on it, right? Gravitational pull. So would this happen, if we dropped a golf ball in deep outer space, would it go faster and faster? No. Why not? Because there's no gravitational pull on it, Okay, so in other words, Earth is involved. There's an interaction between Earth and the golf ball. And the interaction involves energy. Okay, so this energy of interaction, that's what we call potential energy. And potential means it's stored. It's stored energy. For example, if on the floor I had a board with a nail sticking out of it, and if I held a cement block up here, it has stored energy. And if I let go, that energy could be used to pound the nail into the board. So it's potential means stored, right? All right, energy of interaction, potential energy. We're usually going to use U for potential energy, but sometimes we don't. Okay, so now we never had interactions in our system in Chapter 9. Now we're going to include interactions. All right, so now the energy of the system isn't just kinetic, but it's also potential energy. All right, okay, now here's something kind of funny. No, this is right from the book. Kinetic energy is the energy of an object, right? Energy of motion. In contrast, potential energy is the energy of an interaction, right? You can say the ball has kinetic energy, but you shouldn't say the ball has potential energy, Because remember, potential energy is the energy of interaction. So, you should really say, like the ball and the earth or something like that have potential energy, blah, blah, blah. But guess what? We say this all the time, all right? We always say things like the ball has potential energy. So, technically it's wrong, but I think it's pretty much understood, right? When you say the ball has potential energy, you're talking about the system of the ball in the earth, Okay, so there's my confession, all right? We say this all the time, even so it's improper. All right, now this is great, but of course most of the time what we care about is how energy changes, right? So we're basically differentiating both sides of the equation, So the change in energy of the system equals a change in kinetic energy plus a change in potential energy. All right, so now what we want to do is look carefully at this delta U, all right? We want to, we said that delta U is related to the energy of, it is the energy of interaction. So we want to know how it's related to the work, the work of the interaction. And I'm not going to derive it. It's done in the book. But this is a big deal. So the change in potential energy equals minus the work of the interaction. And why is this a big deal? Well, because we don't really have any great way of calculating this from first principles, directly. So we're going to calculate this by using this. That sound familiar? We said something similar to that on chapter 9, when we talked about the change in thermal energy, The change in thermal energy was equal to minus the dissipative work. It's easy to calculate work. We saw that last chapter. So if we can get a relationship like this is easy, so we can figure that out. So it's nice. So here's just a quick example of using that equation. So let's do gravity. Let's consider gravity. All right. So throw something up. Just pretend it's a ball. So we throw a ball up in the air. So what is the ball gravitationally interacting with? Earth. Now I guess you could say it's really interacting gravitationally with me and the floor and all that, but what's a major interaction with the Earth? Okay, so let's use that equation. So delta U gravity equals minus work of the interaction. Okay, now what's the interaction? That's Earth on ball, right? The Earth is interacting with the ball. Okay, now remember there's a minus sign here, right? Okay, so let's do that. So we have minus. Now, what's the Earth? What's the work that the Earth does on the ball? Well, that's the gravitational force, right? And remember, I threw the ball up, right? Okay, so work. So there's the force of gravity. Then there's the distance, delta y. And then there's the cosine of the angle. Now the delta y is this way, force of gravity is this way, so the angle is 180. Okay, now let's keep going. Okay, what's Fg? It's, force of gravity is mg. So we have mg, delta y is delta y. But what's cosine of 180? It's negative. Negative 1. So we have negative 1. And that, of course, just equals mg delta y. Okay. All right, so there you go. Okay. So what's this? The delta ug is ug final minus ug initial. Agree? And what is it? That's equal to mgy final minus mgy initial, right? So therefore, this has to equal that. That has to equal that. So what can we just say? we can just, therefore, ug equals mgy. So that's kind of how you do it. That's how you use that equation to figure out an equation for the potential energy. That's a great, nice example how you do it. And we saw that last chapter, so that's not a big surprise, right? But and it gets more complicated than this, but this is just a nice, easy example of how you use that equation. Okay, now, just a couple of minutes ago, I said that the energy of the system is K plus U. Now, we come across this a lot, and so people decided to give it a name. And so we call this the mechanical energy. And you want to remember that. So the mechanical energy is the potential energy plus, the kinetic energy plus potential energy. And again, what we care about is how it changes. And so the change in mechanical energy is the change in kinetic energy plus the change in potential energy. Now, here's what's so great about this. If we don't have any dissipative forces, so if there's no friction or, anything like that, this here doesn't change. So in other words, the change is equal to 0, right? If it doesn't change, if it's constant, if we say the delta E, that means it's 0, right? Just like calculus, right? If you take a derivative of a constant, it's 0, okay? So this is a big deal, and we're going to use it a lot. So if there's no friction or if there are no other dissipative forces, mechanical energy is constant. Or we can say it's conserved, right? It's conserved. And we're going to use that, and it's going to save us a ton of work. You'll see, all right? So let me just do a quick example. All right. Okay, so this is a tall building. And all we have is a meter stick, right? We have a meter stick and a ball. We don't have a watch. We don't have any way of measuring time. And we're going to ignore air resistance because it's not that tall, all right? And I just made up these numbers, okay? So let's say, I got to copy this. Okay. Okay, so let's say, this is potential energy in joules, this is kinetic energy in joules, this is the mechanical energy in joules. And again, remember, mechanical energy equals K plus U, right? And this is only, and it's conserved. It's conserved because we're ignoring friction. We're ignoring drag. All right, so let's just say we know that at the very top, we have 10 joules of gravitational potential energy. All right, and how do we know that? Well, because remember, this is the formula. We have a meter stick, and we have a ball, and we know the mass of the ball. If we know the mass of the ball, we know G, we have a meter stick, we can measure the height of the building. Good luck in the real world, but anyway. All right, so we know the height of the building, so we know that potential energy is 10 joules. Now we're holding the ball at rest, so what's kinetic? 0. So therefore it's mechanical, 10. All right, now let's say we go down to the middle. All right, the middle. So this is supposed to be the middle. All right, now look. Mechanical energy is constant because we don't have any friction. We're ignoring friction. So this has to be 10 joules, right? Okay, now this is mgh. Here it was 10. If we're halfway, what is the potential energy have to be? It has to be 5, right? We're halfway. So h is now h over 2. So this has to be 5 joules. Now, we want to know the kinetic energy. Kinetic energy is 1/2 mv squared. So you have to know the velocity. Well, velocity is dy dt. You need a watch to measure that, don't you? Yeah, you need a watch or something, some kind of timing device. We don't need a timing device because we know that mechanical energy is constant, it's conserved. So this plus this has to equal 10. So what has to be the kinetic energy? 5. That's cool, right? Who cares about time measuring instruments? We don't need it. Just by mechanical energy conservation, you know it's true. Okay, now let's see. At the bottom, it's 10, right? Mechanical energy is 10. Mechanical energy is 10 everywhere. All right, so right before it hits the bottom, you know, like right before, we're just going to say the potential energy is 0, close enough. So it has to be the kinetic, 10. Okay? So it's nice, right? Simple, 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 you know? Okay, let me review something else for you. I just want to show you another way of writing kinetic energy. Okay, so I said this is mv squared over 2, right? 1/2 mv squared. Okay, let's multiply top and bottom by m. So we put an m here and put an m here. Okay, eventually we're going to learn about something called momentum. Momentum, and they use a little p for it, is mv. Some of you might know that already. But momentum is mv. So here I have momentum squared, right? So this is p squared over 2m. So that's just another equation for kinetic energy, which is really useful. We're going to use it again. So I just want to show it to you now. Right, so this is the one we use a lot, most of the time, but sometimes we use that one too, p squared over 2m. Okay, now Randy Knight, he really likes charts, like bar charts, and he just likes charts, you know, graphs and stuff like that. That's pretty, so here is what's called a bar chart. So this is energy this way, all right? And so at the top, all we had is potential energy. We had no kinetic energy. So 0 kinetic, all potential. And remember, we had 10 joules. So this represents mechanical energy. And it's always 10 joules, right? Because it's constant. Okay, so at the top, 0 kinetic, all potential. Halfway down, we had half and half. So if this is 10, this is 5, and that's 5, right? You could put this up here, and it would reach that. At the bottom, we had 0 potential, all kinetic. So 0 potential, all kinetic, and again, it's 10. So everywhere, you know, you could add the kinetic plus the potential and get 10 because of that. So that's, okay, so that's a bar chart, all right? Okay, now, in every single equation where we have potential energy, it's always written like this. It's always going to be a delta U. We're never going to just, all right, so it's always going to be a delta U, okay? And so this is the only thing that's physically meaningful, the change in potential energy, okay? I mean, yeah, all right? So it's always going to be a change in potential energy. And so what does that mean? I mean, who cares, you know? Well, what that means is that the choice of U equals 0 is completely arbitrary because all we care about is a change. Now, usually, you know, we say that the floor is U equals 0, but we don't have to because all we care about is a change, right? So who cares what's U equal, what's, you know, U equals 0 because all we care about is a change. So that's really important, and I kind of want to beat it to death, all right? I want to show you how important that is. So let me erase. Let's see what this is. All right, so here's the problem. Okay, a 200-gram ball is dropped from the ceiling, height 2 meters, assume y equals 0 at the floor, which is what we usually do. Using mechanical energy conservation, find the speed. So the impact speed means right before it hits the ground. And then draw the energy bar charts. But before we do that, I want to show you something incredibly useful. So here, so we had the change in mechanical energy was the change in kinetic energy plus the change in potential energy, right? And of course, if we have No dissipative forces, no friction, things like that. This is 0, which is great. Okay, so I'm just going to get rid of that. All right. Now this is totally true, but it's not as useful as it can be. So what's delta K? K final minus K initial. What's delta U? U final minus U initial. And that equals 0, right? Okay, so let's put all these negative things on that side. So I have K final plus U final equals K initial plus U initial. Okay, let's just switch them around so we have initial first and final last, you know, just, I mean, who cares? Just switch it around. So I have K initial plus U initial equals K final plus U final. You're going to see that this is a really nice way of writing that, and it just, when you write like this, it makes problem solving really easy, okay? Really, really easy. So another way of looking at, or you can write it like that, or you can write it like that, and whatever, you know, right? This is K plus U initial, this is K plus U final. Super, super important. That's why I'm kind of emphasizing it, right? Super, super important. All right, let's get back to the problem. Oop. Oh, would you look at that? One of the students showed me how to do that. Okay, all right, let's do it. Okay, so here we go. So we're using Randy-Knight coordinate system, might as well. So we have K plus U initial equals K plus U final. All right, and so we're dropping something, right, from the ceiling. We want to know the speed. So, you know, y0, v0, y1, v1, right? So y0 is 2 meters, v0 equals 0, y1 is 0, v1 equals. Okay, so I'm saying this is the origin. Okay. All right, so let's do it. All right, so my initial is the 0. My final is 0.1. Okay. All right. So what's my kinetic energy initial? 0. What's my potential energy initial? Just m g y0. I'll put the numbers in last. And then what's my kinetic energy final? 1/2 mv1 squared. What's my potential energy final? 0. Okay, so I want to solve for V1. So I divide by the mass on both sides, multiply by 2, take the square root. Okay, so there it is. So that's a square root of 9.8 meters per second squared. 2 meters. And I promise you, when you do that, you get 6.26 meters per second. So right before it hits the ground, it's going at 6.26 meters per second. So remember that. 6.26 meters per second. All right. Piece of cake, right? Just, you know, mechanical energy conservation. Love it. All right, now, so that was assuming y equals 0 at the floor, which is what we usually do, but we don't have to. Oh yeah, there's the energy bar chart, right? We started off with all potential energy because we were holding the ball at the ceiling, and we dropped it, and right before it hit the floor, the potential energy was 0, it's all kinetic. So all of that potential energy was transformed into kinetic energy, transformed. Okay, now let's do it differently. Same problem, but now let's assume y equals 0 at the ceiling, okay? And I still want you to use the Randy-Knight coordinate system. So use that, but say y equals 0 at the ceiling, and you do it, please. So pause your video and work it out. All right, we're back. I shouldn't have erased the picture, but I did. Oh well. So there. So this is y0, v0, y1, v1, radiant coordinate system. But now we're saying that this is the origin. Okay? So we're going to say y0 equals 0. And that's the same thing as v0, right? Because we're holding it from rest. Y1, with this coordinate system, that's the origin, is -2. -2 meters. And what we want again is v1. All right, so same old. K plus u initial equals K plus u final. Okay, K initial is 0. U initial is 0, right? Because y0 is 0. So we have 0 plus 0. All right, K final is 1/2 mv1 squared. And U final is minus, okay, mgh, right? mgy1. Well, so it's plus. All right, I'll get to minus in there in a minute, right? But it's plus mgy1. All right, everybody agree? So I want to solve for v1, so I'm going to put that the other side. So we have 1/2 mv1 squared equals minus mgy1. Then I multiply by, okay, divide out the m's. Multiply by 2, square root. Okay, now you're freaking out. You can't have a minus sign underneath a square root? No problem, no problem. Life is good. Square root minus 2, g is 9.8 meters per second squared. What's y1? Minus 2. So you have a minus times a minus. Guess what you get? Same as before, 6.26 meters per second. Kind of makes sense, right? I mean, should Mother Nature, you know, depend on how we set up our coordinate system? Of course not. You know. But look at the energy bar chart now. Initially, we had no potential energy, no kinetic energy, right? So we had, the mechanical energy was 0. So the mechanical energy at the final has to be 0 as well. So the potential energy was negative. Kinetic energy is positive. Who cares if it's negative? Because all we care about is delta U, right? Delta U. So what's the bottom line here? You can choose your y equals 0 wherever you want to. It doesn't matter, because the only thing that's physically significant is delta U, the change in potential energy. Okay, let's quit.